Welcome back. Let's go ahead and take a look at strain hardening now. All right, so when we deform metals, whether that's through a forging process, a rolling process, say for a sheet or something, an extruding process, or a drawing process, any kind of deforming process that results in a shape change of our material is going to result in an increase in the dislocation density. Okay? And this increase in dislocation density results in a strengthening of the material. So if we do this at room temperature, the process is called cold working, and we're said to produce strain hardening. And we saw that in that tension test in the beginning with copper on the first video, where the sample with the higher dislocation density had a much lower ductility. And I said at that time that if we were to actually look at the yield strength, we'd see that it was actually very high. So again, you're seeing that trade-off, high strength, lower ductility. So we want to go ahead and put a number on this cold working, this percent cold work. And so we can do that by simply taking a look at the initial area of the sample, cross-sectional area, and then subtracting off the area of the deformed sample. This will be a smaller area now, divided by, again, the original area, and we'll get a percent cold work. Okay, so usually when we're dealing with percent changes in a property, right, you usually do the final minus initial. This is doing the initial minus the final. Just notice that. Okay, still okay on the bottom. It's over initial. The reason so is because we want the percent cold work to be a positive number, and when we cold work it, we're reducing the area. So they've switched the terms just so we have a positive number. All right. So the issue with having too many dislocations is that they start to actually interfere with each other. So a certain number is fine, and the material can be very ductile. But if you start getting too many and the dislocations start crossing each other, then those stresses around the dislocation core will start interacting with each other, and you get the repulsion we talked about. And depending on how these are slipping, it can actually produce dislocations that can't move. And so that's the mechanism for the strain hardening. It's just too many dislocations start to get in each other's way, if you want. They interfere with each other's motion. So the more cold working we put in, the higher strength we expect out of the sample. So here is our percent cold work number. Right? This is yield strength, and over here tensile strength. You can see they follow the same behavior. And again, the idea is as the cold work goes up, so does the yield strengths, right? And it's very sharp, you can see here for the steel. Tensile strength also increases with percent cold work. So the strength goes up as we expect. But we'd be incomplete if we didn't talk about the trade-off, which is the ductility. So now notice that as the percent cold work increases, the ductility drops. Okay? So that, again, is our trade-off. So this is showing a sample that's been initially cold worked, and then a stress strain test has been run on it. And so you're just seeing visually what the entire stress strain curve would look like. So notice that as the cold work goes up, notice that your tensile strengths are increasing, and also the yield strength, somewhere in here, maybe somewhere in here, is going up. So you're seeing that strength behavior going up. And then also notice, however, that the ductility, which was pretty large on this one, is now getting smaller and smaller and smaller. Okay, that's our trade-off. So let's talk about the what we can do with a sample that has a large degree of cold working in it, and we don't want to leave it in this highly cold work state, which might have too low of a ductility for us. So This is a brass that's been cold worked quite a bit. And you can see these are all steps that are created along the surface of this grain. And so you can see that, this grain has a lot of cold work in it. Well, all of these dislocations mean that you've just created a sample with a very high energy. It has a lot of plastic strain, a lot of deformation in it. And so if we were to heat the sample up to a high enough temperature, what we can do to get rid of all of these dislocations is actually take a piece of that original grain, right? And we basically nucleate a new grain. So the atoms in that area by diffusion get together, they eliminate that dislocation in that area, and we get a brand new crystal forming. Nucleate a new crystal here, new grain. And then as we continue to hold, atoms will hop onto that new crystal because it has low dislocation density, low energy, and then that crystal will continue to grow out. And so all of these spots you see, the darker ones are just oriented such that the light is not shining back, so you don't get the brightness. But these are all dislocation-free new crystals. And so they'll form all throughout the sample. And then as time continues, and I think I've addressed this question, right? Why do the new crystals form? They form because they are dislocation free, and so we've lowered the energy of the deformation energy. The whole crystal doesn't just instantly become with new grains without dislocations. So there has to be some kind of a barrier to this nucleation process, otherwise it would be infinitely quick. Okay, so the barrier is that when I do form a new crystal, I'm forming a new surface around it. I'm forming a new grain boundary. And so the volume of the crystal has a lower energy, but I've also created a defect, which is the grain boundary area. So if my grain is, my nucleus is big enough, the volume term, the lower energy due to the volume, will win over the surface area term, right, which is an area. And so I can form my nucleus. If my energy is too low in the system, then I won't be able to get to this critical size. So that's why there is a recrystallization temperature. You have to go above in order to pick up the diffusion fast enough and to have enough energy to get over this barrier. All right, so if we continue on, this is 8 seconds. You can see the original grain structure is just about gone now. And then finally, we're 100% recrystallized. For our purposes, this 100% recrystallized sample will be considered 0% cold work. And so we've removed all of the cold working of the original sample. And then if we continue to hold even longer, what we'll find is that the grains continue to grow and get bigger and bigger and bigger. All right, so 15 minutes, 10 minutes now, if we kick the temperature up a little bit, now you can see that these grains are getting much, much, much bigger. These sharp lines that you see are interesting because these are twin boundaries. They said in FCC materials in your text that you can get some growth twinning, and here it is. So as we're growing these new grains, we get this twinning process. Right? And so each of these is a twin. So the crystal here in the dark has twinned, and its twin area is bright because it is angled. Now it's for good reflection, and then it twins back to the original crystal direction. And that's what you're seeing through all of these, is this sort of twinning and then twinning back. Okay, so all those straight lines are twins. All right, so the grain growth process is a diffusion process. And so if we take a look at two crystals or grains near each other, the larger grain or the lower energy because of maybe the not having high defect density in it, but one grain is going to be of a lower energy. I'm going to have another grain that's going to be of a higher energy. And so what we can do is get atoms from this high energy grain to hop across into the low energy grain. And so as these atoms hop across, then this grain continues to grow and eat up that smaller grain, say, if this was a large grain structure. And that's the grain growth process. We're eliminating the total number of grains in our material and then allowing some of them to get really big. So we can characterize that. And in fact, the diameter that we can expect for grain growth goes by a constant that again is a fitting parameter, our time, and then D0 is the original grain size at our time t equals 0, and then n is another fitting parameter. And typically n is around 2. All right, if you get a problem, and I don't remember if I gave you this one, but if you get a problem in the text that wants you to solve this grain growth equation and it doesn't give you n, there's one little phrase in your text that says you can assume n is equal to 2 for most cases. So I'll always make sure I give you this n value. But if you're not given it, you can go ahead and put 2 in. All right, so this is the grain diameter now versus time at various temperatures. All right, one of the things I want to take a second and talk to you about is the way to interpret plots like this when you see them in the textbook. One of the things I might ask you, for example, on an exam is I might remove these temperatures. And I might ask you which of these curves is at the lowest temperature or which of these curves is at the highest temperature. And I don't want you to memorize all the plots in your text to answer something like that. I want you to be able to think about what's here and be able to rationalize where the higher or lower temperature sample is. So the principle here is that you would expect the grain diameter to be largest at the same time for higher temperatures, right? Because higher temperatures means that my diffusivity, my diffusion coefficient, right, is larger at high temperature. So diffusion is faster at high temperature. I think we all know that now. And so if it's faster, then I would expect my grains to grow quicker at the higher the temperature. Okay, so that's the principle. Now, the way that you would then go ahead and interpret it on something like this is to go ahead and in this case, the time axis. I usually do this on the y-axis. This particular one, the way I've explained this, it probably works on the time axis. But you want to fix something. You either got to fix the diameter and interpret the time, fix the time and interpret the diameter. So let's go ahead and fix the time. So I'm just going to draw a line up here to remind me that the only thing I care about is these values here along this line. So I've got a fixed time and I have the size of the grain at that particular time. And then notice this one up here is a very large grain for the same time that it took this one down here to form a fairly small grain. And so that means that this one must be the high temperature, right? Because it's forming a large grain at this for the same amount of grain growth time. So that's how I'd like you to be able to interpret these. So when you see any of these kind of plots in the text, make sure that you can take the labels off and understand what is the principle that's going on in this plot so that if I give it to you, you'll be able to choose the higher or lower. All right, let's take a break there. And then I'm going to come back and walk through a design example for us.